So very quickly, writing rate laws for reaction mechanism using the slow step, the rate determining step. Now that's very easy if the first step in a proposed mechanism is the slow step. You remember that the rate law for an elementary step, which this is an elementary step, each of them is, okay, these are both elementary steps. If the first step is the slow step, you can write the rate law directly from the molecularity of that slow step. So our rate law would simply be K, and there's two nitrogen dioxides, so that would be NO2. It's bimolecular, and so it would be second order in nitrogen dioxide. Okay, so if you have a slow step for the first step in a proposed mechanism, you can write the rate law for that slow step based on the molecularity of that first step. Now, it has to be consistent with the experimentally determined rate law for the particular reaction. We did that, and we discovered that the rate law for the reaction is in complete agreement with the rate law for the first elementary step, which is the slow step, which is exactly the same. It's second order in NO2. All right, so let's write the rate law for a reaction mechanism when the slow step is not the first step. Now, we still operate on the principle that the slow step or the rate law is going to be based on the molecularity of the slow step, which is now the second step. And one of the things that you want to recognize here is this first step is a fast equilibrium, just means that the rate in the forward direction is equal to the rate in the reverse direction, and it's producing an intermediate. You can recognize the intermediate because it's produced in the earlier step, that's B, and it's consumed in the second step. And we've labeled the rate constant for the first step, K1 for the forward direction, K minus 1 for the reverse direction. That's conventional. And then we can label the rate constant for the slow step as K2. So the first thing we want to do is let's add up the first and second step. If we're adding up the first and the second step, the first thing we're going to do is we're going to cancel the intermediate. Keep in mind, B is an intermediate. All right, so if we add these up, we get 2A plus D is equal to E plus C. So here is our overall reaction for this particular problem, okay, for this particular mechanism. And what we want to do is we want to write the rate law based on the slow step, but we notice that B is an intermediate, and as an intermediate, it can't be in the rate law. So let's go ahead and let's treat step 2 straight up and write a rate law for it. So here we have rate is equal to K2 times B times D. All right, so that's fine, except that this is an intermediate. Now, if we go up to the first expression, or the first elementary step, we see that this is a fast equilibrium, meaning the rate forward is equal to the rate reverse. And so these two rates are equal to each other, so I can go ahead and I can write rate forward is equal to rate reverse, and here's the rate law for the forward reaction. It's K1 times A, based on the molecularity, the coefficient is 2, it's going to be A squared, equals K minus 1, that's the K value for the reverse reaction going the other direction, and that's going to be times B times the concentration of C, which is the other reactant going in the reverse direction. So what we're going to do is we're going to go ahead and we're going to solve for the intermediate so we can write the rate law in terms other than the intermediate, because I can't go to the shelf and pull off any intermediate B to write the rate law for. It's not a reactant. So I'm going to go ahead and I'm going to divide both sides by K minus 1 times C. And when I do that here, the C cancels, the K minus 1 cancels. Over here I have K minus 1 times C. Now, this is equal to B. So now I have the concentration of B in this reaction is equal to K1 times A second order divided by K minus 1 times C. And that is equal to B. So I'm going to take this value that I've just determined and I'm going to substitute it into the rate law for the second step wherever B is. So that's going to give me rate is equal to K1, and then don't forget the second reaction forward has K2, so this is going to be times K2 divided by K to the minus 1, and then this is going to be times A second order. Don't forget the D, that's still there from the slow step right here, that's included, and then divided by the concentration of C first order. All of this, all this K stuff, K1 times K2 divided by K minus 1, I'm just going to go ahead and simplify that, and I'm going to say K, and then I'll have A second order, D, and divide that by C. And that is going to be my rate law for a slow second step.